Hello, here is the numerical solution to the learning catalytics problem from May 5th. There's a bar here. It is supported by a pin at the bottom, bolting it to the wall, and by a wire or cable that pulls the tip of the bar that way toward the wall. So there's a vertical wall here. There is a weight, of course, to the bar because it has mass, and those two forces, the weight vector down and the pull of the tension in the cable over here, are producing a torque about the pivot point. So when we set it up, I reminded you that counterclockwise torque is positive, and that's what the wire tension is producing, and clockwise torque is negative, and that's what the weight would be producing. So you want to play with your pencil. The key idea with torque is that you multiply a distance times a force, but you need to put sine or cosine in there so that you have the perpendicular distance from the pivot point to what's called the line of application of the force. So I know this has to be balanced because it's not falling down. So my torque is going to equal a great big sum of the counterclockwise plus the clockwise torque. When they sum to 0, I can set them up to be equal to each other, as we did with seesaw problems all year. So we set R cross F, in this case, for this whole radial distance times this force. So that's 21 meters times my unknown tension pulling the tip of the bar. And I multiply times the sine of 45. This 45-degree angle was given to me, but the perpendicular distance from here to that line of action of the force is right there. And that is opposite a 45-degree angle by alternate interior angles. So this is how I get the torque for the cable pulling to the left. On the right-hand side, the weight vector is pulling the bar down, producing clockwise torque, but it exists right there at the center of mass of the bar or the beam. So therefore, that force distance is half of the length away. And then I'm going to multiply times mg because that's the magnitude of the force. So you can see I have an equation now that has only one unknown in it. To make my calculator life easier, I'm going to cross off 21 meters because it's on both sides. I'm going to wind up dividing cosine by sine. The sine divided by the cosine for a 45-degree angle is 1. So it's 1 if I turn it upside down also. So what I can see here is that T, that force in the cable, is going to equal 27 kilograms times 9.8 divided by 2, because these are the only things that survived. So if you put that in your calculator, 27 times 9.8, please go ahead and do that with me. Divide that by 2, you get 132.3 newtons of force to the left pulling. All right, I got that far with torque. That's not going to help me get the whole problem, which is what is going on right there at that pivot. What is that pivot doing to the bar? So I'm going to have to go to force. So we did that in class on Zoom. So I'm looking now at net force, no longer looking at torque. And I figured that the force in the x direction has to balance because I have only this force to the left, and then whatever the bolt or pin is doing right there, the force in the x direction is going to have to equal the x component of the force of the pin. So once I've figured that out, and I now know that's 132.3 newtons, I've got a component of the pin or the bolt figured out. Now I need to go to the y direction. In the y direction, the ups and the downs must balance also. So whatever the pin is doing in the vertical direction is counterbalancing what the weight is doing. So therefore, I'm going to say the sum of all forces in the y direction is 0, and I'm going to set these two things equal to each other. So once I do that, that means Py, going up here a little bit, is going to be equal and opposite to 27 kilograms times 9.8. Now, you may ask yourself, why not just go ahead and find P right now using sine or cosine? And the answer is pretty complex. That picture was complex. It had kind of a strange shape in there. I'm not at all sure that I know what the angle is or what exactly is going on there. So the safest thing to do is get these two separate components out of mathematics that you're sure of, and then use the Pythagorean theorem on them. So this means Py is 264.6 newtons. So I have a Py like that, and I don't even need to know the sign of it if it's going into the Pythagorean theorem, because that is going in right there, and this is going in right here. So the pin is equal to the square root of 132.3 newtons squared plus 264.6 newtons squared. If I get those things into my calculator, and then I take the square root of the whole thing, I get the correct answer. The pin is supplying 295.8 newtons of force. So in order to get that, I had to use torque and I had to use force. And that is a great problem because it's about equilibrium. When you have equilibrium, you have to have a net torque of 0 so that the bar is not spinning, the beam or the bar. And you also have to have a force linear translational equilibrium so that the bar is not going up or coming down. So there's a great torque problem for you, and that's from learning catalytics.